Our next speaker is Jonathan Crawford. He's a student working with John Yu and Chengwei Lei on blockchain database for underground aquifer protection in oil fields. He's going to be giving us a video recording and then answering questions after that.
Can everybody see it?
Yes, we're good.
Hello, my name is Jonathan Crawford, and I will be presenting the underground injection control process using a blockchain. In this presentation, I will be going over 3 parts: research paper outline, what the prototype looks like in workflow, and future implementations. Part 1 is the research paper outline. For over 60 years, California's oil and gas companies have been injecting gas and water into hydrocarbon-bearing formations for the purpose of production enhancements and waste disposal. Currently, there are about 55,000 injection wells in California. For each barrel of crude oil produced, 15 barrels of wastewater is also produced. 2/3 of this wastewater needs to be re-injected into the original underground reservoirs, which comes to about 60 million barrels per day. The Environmental Protection Agency designated exempt areas for wastewater injection. These designated areas allow wastewater to be injected as the water in the area is unsuitable for human consumption. Due to the increase in demand in California for fresh water, authorities require a higher standard in underground water management. In 1977, the U.S. Clean Water Act was approved by the U.S. Congress. The CWA is the primary federal law in the U.S. governing water pollution. Its objective is to restore and maintain the chemical, physical, and biological integrity of the nation's waters. The EPA established the Underground Injection Control Review and Execution process to ensure the injection process complies with the CWA's laws and regulations. The current UIC review process leads to expensive and unnecessary delays. 3 difficulties exist that create these delays: distrust of the data, lack of uniformity, and slow dissemination of information. The first problem is data integrity. The current system has technicians manually inputting the data into the system. Not only is this required for the initial integration to the system, but also anytime the data needs to be transferred to another organization's database. The second problem is exacerbated by the first problem, the lack of a uniform system among different organizations. The current process requires multiple organizations to review the data from the oil well injection site. However, not only does each organization only care about certain parts of the data, but each organization stores its information in a different database system. This means anytime the data is transferred between organizations, the technician has to once again input the data manually. This makes errors much more likely and decreases the integrity of the data. The last problem is the overall time it takes for each organization to get the required data pertinent to them. Due to the first 2 problems, each organization has to go through additional verification steps to ensure the data they have is correct. This takes time, and for a project of this nature, the longer the approval process takes, the more costly it becomes to the entities that actually use oil well injection sites. This also requires each organization involved to spend unnecessary resources on an inefficient UIC approval process. In order to solve the problems with the UIC approval process, we propose using distributed ledger technology, specifically a type of blockchain, to replace the current system. A blockchain is a structure that stores transaction records on a network connected to peer-to-peer nodes. With the cryptographic nature of the blockchain, the data transferring process maintains data integrity, solving the first problem. The blockchain structure also utilizes a decentralized distribution of information, meaning that each node will receive a copy of the data the moment a block is input into the system. The fact that every node in the network receives each block means each organization has whatever data they need the moment it is created in the chain. This decentralized distribution of information solves problems 2 and 3, allowing the quick transfer of information and instant access to what data is needed. We use public domain data from the state regulatory agencies to populate the oil well states. Our smart injection project was implemented using Corda as the distributed ledger technology and backend. For the GUI and front end, we used Angular. Unlike something like Bitcoin, Corda's blocks are shared facts between nodes. Each fact represents a state, or in our case, an oil well. The state creates transaction whenever it is created or changed. Thus, a block on the other blockchains can be seen as oil wells in our model. Corda saves all transactions, so it's easy to track the history of an oil well by bringing up all related transactions. The design for the prototype model includes two main entities, CalGEM, the regulatory side of the process, and a generic oil and gas company that would operate the wells. By using Corda as a backend and underlying DLT, we also only share information on a need-to-know basis. This means that each entity can only see information that they actually need to see. This is particularly important for oil and gas company side. Even if the number of oil and gas companies involved increases, they wouldn't have access to information of others on the network by default. The architecture of the prototype is simple and scalable. Each site would have their own Corda node that they could access using a web server. The Corda node would store data on a local relational database and use a doorman service for permission access to the network. This keeps each node lightweight and makes it easy to add more nodes on a permission basis to the network. Corda implements smart contracts to ensure data is accurate. For example, if an oil well is submitted to CalGEM for approval, the smart contract can ensure constraints are met prior to the transaction being approved. In the diagram shown here, each entity contains a Corda node, web service, relational database, and API gateway. Users internal to the organization would use the web service to submit transactions to the Corda node via API gateway. They would also have access to the relational database Corda uses to store information via the vault service provided by Corda. Users that are part of other organizations would communicate using the Corda node's messaging services. This is how transactions are signed and communicated through the network. The shared services are inherent to all Corda nodes and thus accessible by everyone on the network. These include network map, vault queries, and notary nodes. A Corda node is made up of several parts. The RPC server and RPC client allows remote access and control of a Corda node. The API gateway allows users within an organization to access the node and submit transactions. The messaging service allows nodes to talk to each other securely on the network. Corda uses notary nodes to approve the transactions on the network as opposed to a proof of work, which is made to be slow and resource intensive. This makes Corda lightweight compared to other DLTs. The notary service provides digital signatures ensuring the data on the network is authenticated and accurate. The network map service manages membership of the network. The results of this work led to a working prototype. With a smart injection prototype, companies could store and submit records on a unified system with ease. Each company also has access to the data they need when they need it in order for the UIC review process to be fast and efficient. The entities within the network do not have to worry about data leaks as everything is on a need-to-know basis and nothing is shared until it has to be. This means an oil and gas company can store their well information on the network and when they are ready, share that information for approval. The prototype also demonstrates the data flow, immutability, and security of the model. Part 2 is the current implementation. In the prototype, two major entities exist, CalGEM, the regulatory portion, and a generic oil and gas company. We will go over the well operator portion in a typical workflow. The CalGEM side of things would remain almost identical in what they see, the only difference being the added functionality of approving or denying projects. The first thing a well operator would see after logging into a node is the dashboard. The dashboard allows the well operator to view and create projects and wells. From here, the well operator might view pending projects, check on created wells, or create a new well. Normally, a well operator would have a list of wells that they need to get approved, so the first step would be adding them to the system. The Create Well page is a simple form. Data is filled out and attachments are used for more complex forms of data such as wellbore diagram. By using drop-downs in some areas, the system can make sure the well operators are conforming to the appropriate standards. After the well operator has a set of wells, they can view those wells to make sure everything is correct. They can also update the wells if something is missing. The process of updating wells is restricted once it's sent to CalGEM for approval. Once the well operator has all the wells they want to submit to CalGEM, they would create a project grouping those wells together. In day-to-day operations, projects are what both well operators and CalGEM processes. Thus, if a project is approved or denied, the status applies to all the wells within. Some exceptions do apply but are not currently represented in this model. The project interface is straightforward. A project name is entered, wells are chosen from a list of wells that currently do not belong to any project, a review of the data is shown, and finally the project is submitted to CalGEM. After the project is submitted to CalGEM, no changes can be made to the project or the wells by the well operator. Finally, the well operator can view all pending projects or click on individual projects to see specific details. As mentioned before, the CalGEM side of things is almost identical. The key differences are that CalGEM wouldn't create or update wells or projects and have the ability to deny or approve projects. Part 3, Future Implementations. In this section, I will go over some of the current restrictions of the prototype model, additional features we want to add, and a scaled-up model. Some of the restrictions of the current model include a need for human evaluation. Although smart contracts can enforce certain restraints, an engineer still has to review the data for each well and verify that everything is correct and acceptable. So even though the prototype can be significantly faster, it will still not be purely automated. The current model is also very rigid. If there's a problem with a well inside a project, CalGEM would have to deny the project so that the well operator could update the well and then resubmit. Smart contracts can reduce errors in the data by enforcing data validation and other constraints, but there are cases where the fix could be simple and shouldn't require a full loop of the system to correct. The model also does not have any service company represented. Service companies are used by oil and gas companies as third parties to test and evaluate wells. The data from these companies is part of the package that is eventually sent to CalGEM. Adding in a service company would be as simple as adding another node. However, the backend currently does not support the new functionality that would have to be present. One of the things we want to add is a messaging system. The backend currently has this functionality, but the front end has not implemented it yet. This system would allow CalGEM and well operators to communicate with each other about specific wells or projects and alleviate some of the minor errors or corrections needed in the UIC approval process. Another aspect is updating what can and cannot be changed by the well operator depending on the status of the well. Allowing the well operator to make minor changes to the well might also alleviate the need for a project to loop back into the system. The updates would have to be looked at and decided by both agencies on what can and cannot be updated during the approval process. The scaled-up model is the addition of the service company. Defining the exact relationship between the three entities would only have to be evaluated once, after which adding other oil and gas companies or service companies to the architecture would just be a matter of setting up the node. More complex functionality could also be added in the future as the need arises. This concludes the presentation. Thank you.
Thanks, Jonathan. So we have time for questions. Please raise your hand or write in the chat, and I'll. So, Jonathan, I have a question. So the next steps, what are exactly the next steps for this project? Where are you going?
Right now, we just finished deploying the backend to an AWS server. So we are in the process of deploying the front end. After that, it's actually handing it over to the oil and gas guys, Dr. Yu, Jason Cotton, so they could actually get their hands on it, start playing with it, see kind of how it feels like. And then once we have the simple model ready, then we can start actually adding the features, adding additional workflows, things like that.
Yeah, Jonathan is correct, and Jonathan already put it in his talk. Actually, for this one, this is a preliminary prototype, and there's some additional work that we need to enhance the blockchain applications. That he mentioned it, and I really hope we can make the blockchain networks more flexible, more useful, more applicable to the industry. That's the next step we want to go.
Other questions? Okay, well, thanks again, Jonathan. That was great, and wish you all the best in the next steps.
All right, thank you so much. I appreciate it. appreciate all the students' hard works and our team. We are working very good. Thank you.
Great. It's always good to see students hard at work.